Hello everyone, welcome to SmartGridCom 2020. My name is Yunshan Liu. I'm going to present the SSEN. This paper is about the short-term wind farm generation forecast. From the real wind generation data, we observe that the wind farm generation shows the different seasonality and the different dynamics of the different classes of wind turbines. To deal with such heterogeneous dynamics of wind farm generation, so we propose the seasonal self-evolving neural network model. This work is collaborate with CSUSB, NTU, ASU, and is supervised by Dr. Lei Yang from the University of Nevada, Reno. As all we know that United States has its RPS targets, which stand for the Renewable Portfolio Standard, a requirement on retail electric suppliers to supply a minimum percentage or amount of their retail load. For example, in the state of California, 10 years later, 50% of the energy should come from the renewable energy. Then let's switch to the pie chart of the RPS targets. So as you can see, the wind energy accounts for the large proportion of the renewable energy. As you can see the total installation and the newly installation in different years, the wind energy is growing year by year. However, wind power is not that easy to use. There are several challenges. First, it's the variability. So wind is a kind of a random and discontinuous energy, which means that you might have a great wind power output in the current several hours, but in the later several hours, this power drops to zero. And second, you can see this CDF graph where x-axis is the power of the wind turbine and the y-axis is the probability. So this shows the dynamic of seasonality and non-ramp, ramp up, ramp down, and also dynamics with the different classes of turbine. So when you want to have a high penetration integration of wind power, that will have a big problem. Recently, the researchers are focusing on how to develop a more accurate forecast model. The existing method can be categorized as below. For physical model, physical approaches have good performance over midterm or long-term wind forecast. The approach requires a not very large amount of computation and typically need the aid of the supercomputers. They are suitable for the forecast of newly built wind farms lacking of historical observation number. However, the forecasting accuracy of this approach is limited by the precision of numerical weather prediction and the correctness of the wind farm models. For statistical model, we have autoregressive and Markov chain models. Since the approaches are based on the inherent persistent nature of wind generation, they are well suitable for the ultra-short-term wind generation forecast for very limited meteorological information. And we also have the artificial intelligence related model, such as SVM, ANN, LSTM, or all kinds of neural network related models. It's also good for the short-term forecast, but the drawback is the parameter tuning, which is always a challenge task. Besides, for those models, ramps are always overlooked. Then we also have some other decomposition-based models, such as EMD and VMD. Those models can handle different dynamics to some extent. However, it is tricky to decide what is the appropriate component number for decomposition, why the performance of the models are affected by those numbers. I will introduce the data we used in the paper. We have two classes of turbine. One is GE, one is Mitsubishi's. Their number and the rate capacity are different. And in the plot, which is the power output versus the wind speed, their cutting speed are also different. And for each classes, A meteorological tower has collected wind turbines' instantaneous power output for both GE and Mitsubishi's, and also the wind speed and the wind directions. Those information has recorded every 10 minutes for the year of 2009 and 2010. So from the real wind generation data, the key observation is that wind generation exhibits the non-stationality and seasonality and the dynamic of a non-ramps, ramp up and ramp down. Events are different across different classes of wind turbine. The challenge is the ramp events. As you see this plot where x-axis is the time and the y-axis is the wind power generation, there is a ramp up during the midnight. This might due to some strong weather events can cause very large ramps in the wind power that prove it is very difficult for the power system operator to manage. However, most of the AI-related model overlooks such events, even it is real. So in the dispatching task, when there are ramp ups, renewable energy is wasted. When there are ramp down, power outages might occur if there is insufficient reserves. So based on such key observation, we developed different models for different seasonalities from season 1 to season 4. And also we separate the ramp up and ramp down. Suppose we have the historical data contains the wind speed, wind direction, and several lags of the wind power. Those data are classified by the ramp classifier. Thereby, we have the ramp up, ramp down, and non-ramps data, and followed by the self-evolving neural networks for the ramp up and ramp down, where the non-ramps data is further split into 4 datasets for 4 seasons. Then we leverage the neural evolution of augmenting topology, which is neat, to train the neural networks, which involves a neural network using a genetic algorithm to find best weighting parameters, and the network topology using the classified data. Therefore, 6 for GE and 6 for Mitsubishi's, totally 12 neural networks are trained in order to capture different power output of dynamics of the GE and Mitsubishi's turbine. So when the model is well trained, so we use recent wind farm generation data as the input and got the short-term forecasted output. Under this design, the model will select the appropriate neural networks based on the GE and Mitsubishi's turbines' recent power output to predict the short-term wind farm generation. So let's take a closer look on the ramp classifier. Suppose we have the power versus time curve, and we have 2 points. The time gap between them is L. And we want to define what is the label for the next time step. As we mentioned, there are 3 labels, right? So the ramp up can be the power difference greater than the positive threshold times of a maximum power, where the index class can be either GE or Mitsubishi's. And ramp down is the power difference smaller than the negative threshold times of maximum power. And the non-ramp is the power difference between the negative threshold times of maximum power and the positive threshold times of maximum power. SSEN contains the several different models and is based on the genetic algorithm. The goal of the neural network is to minimize the prediction error by maximize the fitness function. So here is the flow chart for this algorithm. So first, the algorithm starts and generates the initial population of the genes. Each genes represent a neural network. So some genes are selected and the different parts of the topology are extracted and recombined into a new gene. In the mutation part, it will randomly add some connections and some nodes for some neural networks. And because we have a large population of those genes, so after such operations might generate some similar genes. This part will cluster the similar genes and label them as different species. And the next, those genes are evaluated by the fitness function. Only the genes with high fitness values are reserved. And also it will check if there are some species fitness value do not increase after some number of generations. If this happens, those species will be ignored. We will check if the generation number or the fitness value condition is satisfied. If it is not, then it will come back to the evolving process. If satisfied, this algorithm stops. We'll give some examples to show how this process works. So first, it will generate a population of genes, and each gene represents a neural network. So you can see like this. So here is a simplified neural network. So here we have the input of wind power, wind speed, wind direction, and the output is the prediction of the next timestamp. And next is the crossover part. Suppose we have a two neural network, and then we will extract the different part of their topologies, and then link them together, and we got a new neural network, which is completely different from the previous two. Next is mutation, so we can randomly add node or connections. So you can see we can randomly add the connections here in the green line. And also we can add node number 6 here. So we need to disconnect the previous link and replace by the new. So for speciation, it is calculated by the similar functions. So you can see those two neural network from the topology perspective. So these two are different, but the next, they are the same. Then also we can get the output for the neural network, and it can be expressed by this. So H is the mapping function, mapping from the input of the recent observation of wind power, wind speed, wind direction, to the output of the prediction. The H here is determined by the topology and the weight of the neural networks. As the previous process done and elite gene is achieved, we need to run several times and got the several elite genes. And from these several times elite genes, we choose the best elite gene for each neural network for the point forecast. So for example, if the input can be the ramp up type, and also it can be the ramp down type, or it can be the non-ramp type. So for the non-ramp type, the prediction is achieved by the related seasonal neural network. So the output can be expressed by this. And the X class subscript I, the I is ranging from 1 to 6, which denotes the 6 data set. So subscript from 1 to 4 corresponding to the non-RAM data set for 4 different seasons. And X class subscript 5 is for the RAM up, and the X class subscript 6 is for the RAM down dataset. Using the selected neural network, each class of wind farm generation forecast is achieved, so the final prediction output is to add the GE and the species together. To efficiently integrate the wind generation, distributional forecasts are always required to manage the uncertainty. So during the training of the neural network, we obtain many genomes and we pick the best genome for the point forecast. To obtain the distributional forecast, we can leverage those forecasts given by all of those genomes. For example, we have the first best genome, which is the green line. And also we have the second best genome, which is the blue curve, and so on. Then we have a region that covers that point forecast. Mathematically, So we can use a set to represent such genome. And also we assume the prediction error of the point forecast follow the standard normal distribution. So the mean and the variance can be estimated by this. Based on this assumption, we can obtain 1 minus alpha confidence interval of the point forecast, where the z denotes the points where the cumulative distribution function of the standard normal distribution equal to 1 minus half of alpha. In the case study, we use MAE and RMSE, which is the error power of 1 and the error power of 2. For the model parameter tuning, negative and positive threshold and a capital L will impact the prediction performance. So we leverage the threshold of 10, 15, 20% changes in 1 hour, and we choose the threshold for our data through exhaustive search. For capital L, we pick the best value based on the MAE under different values, and we observe that when the feature dimension is equal to 9, give the best MAE. We do not try large L. It is because, first, the running time increases significantly for the large L due to the complex evolution process, and second, bad features may be involved due to the non-stationality of the wind power outputs. We want to see what is the performance of our model in different cases. The distributional forecast can be seen in this figure, where x-axis is the time and the y-axis is the wind farm generation. So the blue line is the ground truth, and the red dotted line is the point forecast. And the gray region is 95% of prediction interval. The reason why we choose this time period is because there is a mildly ramp rate is about 6 megawatt per hour. January the 16th, there is a remarkable ramp rate up to 32 megawatts per hour from the midnight to 15 minutes past the midnight. In February the 7th, there are both ramp up and ramp down in 3 hours, with a ramp rate of about 13 megawatts per hour. Because there is 95% of the prediction interval, so there might be some point in the point forecast exists the gray region. As has been shown that our model works for both mildly ramp rate, remarkable ramp rate, and also in the time span that contain both ramp up and ramp down. Then we want to see how is our model quantitatively compared with other models. We compare with other methods, such as non-neural network-based model, AR, Markov chain, and SVM enhanced Markov chain model. And also we compare with the neural network related models such as LSTM and the self-evolving neural network model without separating RAM and non-RAM events to see how different the performance is. Let's see the comparison of 10 minutes point forecast result. Compared to non-neural network, our model performance has increased at least about 23% for the entire year and 12% for the all RAMP events in terms of MAE measure. Compared to neural network model, for both entire year and RAMPs, our model has increased about 4% by MAE. Let's see the comparison of 60 minutes point forecast result. Compared to non-neural network, our model's performance has increased at least about 10% for the entire year and 11.2% for the all RAMPs events in terms of MAE measure. Compared to a neural network model, for both entire year and the RAMPs, our model has increased about 5% by MAE. The takeaway here is we use self-evolving neural network to deal with the challenge of parameter tuning. And second is we use the multimodal to handle different dynamics of wind farm generation. In the future work, we will refine the RAM classifier instead of using the fixed threshold, but more adaptive ones. Thanks for watching.